Good morning, friends. We were discussing about how do I locate wing, where do I locate wing, should I give a setting angle in the wing or not, what should be the size of the tail, horizontal tail, whether we will give a tail setting angle or not. For meeting two conditions, one is the aircraft should be statically stable, that is dCm by d alpha should be less than 0, and Cm naught should be greater than 0, so that I can trim at positive angle of attack. And how we started as far as conceptualizing the design, we said, okay, I know Cm versus Cl will be something like this, and this slope dCm by dCl is nothing but minus static margin, and static margin we define as if this is the neutral point and if this is the CG, then this difference is static margin, and it is expressed as some percentage of chord. If I say 15% static margin, that means this gap is 0.15 C bar, mean aerodynamic chord. C bar is mean aerodynamic chord of the wing. So that is fine if we are designing it like this, that I want 15% static margin. Generally, aircrafts will be designed between 5 to 10 or around that percentage. But at a conceptual stage, you take a conservative value, then you will find Murphy law will apply. You will have a lot of difficulty in handling CG. Once I know Cm versus Cl, I can easily start visualizing it in terms of Cm versus alpha, where this slope now will be dCm by d alpha. And this alpha I can easily get from lift equal to weight. I know what is CLI requirement is there. Then on CLI I write equal to CL naught plus CL alpha into alpha. So I can get alpha. Please understand, during the conceptual stage, you are assuming that all the lift is coming from the wing. But we know in actual practice, some lift will come from fuselage, some lift will come from tail. But at a conceptual stage, because the wing is dominating as far as lift is concerned, I do this approximation. I translate this to Cm versus alpha. And now I see that I need to have a particular value of Cm naught here, which needs to be generated through either wing, how I am keeping the cambered wing, if I am keeping the AC of the wing little ahead of CG of the aircraft, I know this gentleman becomes positive, right? But this will always remain negative for a cambered aerofoil, but it becomes positive for a reflex aerofoil. So camber has a positive camber and negative camber. When I am saying cambered aerofoil, in a conventional sense, the Cm AC of the wing will always be negative. Since I want some positive value of Cm naught, I have to nullify this contribution. So one way I can nullify this by making this gentleman positive, that is, I put AC of the wing ahead of CG of the aircraft. And second thing is, I come here, I try to see that even if I put this 0, then I can manipulate or generate a positive moment by giving IT negative. And that is called tail setting of that horizontal tail negative. But if you want to enhance its contribution, then this gentleman, VH, tail volume ratio, will play an important role. And that is why for a designer, he operates through tail volume. First question, he decides how much tail volume I should take. Right? And you could see immediate effect of tail volume. The moment you increase tail volume ratio, your neutral point moves backward and it becomes more and more stable because VH is here, right? So for a designer, he will always try to use this information for a different similar aircraft, what is the tail volume ratio? He picks up that number, right? Before going to use historical data, let us also see, once I write this expression, Cm naught of the aircraft is Cmac of the wing, do I know it when I am doing conceptual design or not? Answer is yes, because at some stage we have chosen an aerofoil, right? Okay. The moment I know the aerofoil, I know what is Cmac of the wing. Do I know CL naught? Yes, I know CL naught because I have chosen an aerofoil, maybe a 6 series aerofoil, maybe a laminar aerofoil. Then the question comes, do I know XCG of the aircraft? That is the most difficult part. So again, we start taking the advantage of historical data, and we know this will be between 40% or maybe between 38% to 45%, around that range from the leading edge or from the propeller here. This distance you will find roughly 38 to 45% of the total length will be the CG. These are numbers, right? Okay, and a good designer will see from different configuration where exactly CG is located. Just to give an example, as I was talking about CG, the CG of the aircraft will depend upon the type of payload you have or type of passenger configuration you have. If you see aircraft where the passengers are sitting here, like your Airbus, Boeing, all those, so there is a tendency of CG going backward, right? Okay. But if you see an aircraft like your Cessna 206, where most of the passengers are confined here, so this portion is much emptier. So there, you won't be surprised if this CG is between around 25% of the total length. So it is important to see what type of aircraft you are doing. So what I should do is, instead of 38%, right, let me write 25% to, let's say, 40%, which is a little higher side. Let me correct this. But this is a guideline. My request is always you give a lot of weightage to a baseline airplane, right? Okay. Because every aircraft has got its different mission requirements, and accordingly you will find CG will play havoc, right? Unless you are careful about CG, you will have to change many things at the final moment. Let us check for Cessna 206. We have Cessna 206, where I could see total length is around 28 feet, and your CG is roughly, which is around 6 feet. So how much it comes? 6 by 28, that is 3 by 14. So 3.02, around 22%, right? Okay. So this is the most forward CG. Most aft CG is little aft. So around that. That's why when I write 25 or 40, don't take me to court. Sir, it is 22% there, right? So you are responsible to see what type of configuration you are doing, because final aim is you want to carry a cargo, right? Carry passenger, carry cargo. So that is more important. You have to first see the layout, how you are going to put all those things, and then you start thinking of wing, etc., right? Okay. So there is always a conflict between a layout engineer and a aerodynamist or a flight mechanics or design engineer. It's a part of life. Okay. So let's say in a simplistic manner, we only could tell at this stage that you have to be very careful about CG. It is better you see a lot of statistical data for different types of aircraft. One should put a lot of care here. Okay. Now I was discussing how many things we are having at our hand during conceptual stage. Since we have decided aerofoil roughly, so you know this value, you know this value, you know XAC of the wing, and also CL alpha tail, that is, you select some symmetric aerofoil. We'll discuss that. We generally, it is that you use a symmetric aerofoil tail, but its aspect ratio should be less than the wing aspect ratio, just to ensure that tail stalls later than the wing, right? These things you know. I also have got a fairly idea about this number, right? So what is important, who will save us is VH. And what is VH? The tail volume ratio. Why I am giving so much weightage to VH? Let us see that. VH is tail volume ratio. I am talking about horizontal tail. Ideally, if this is the wing, this is the tail, this is the AC of the tail, right? And let's say this is the CG of the airplane. So LT, the tail moment arm, is defined by the distance between CG of the aircraft and the AC of the tail, right? But the whole problem is at this stage we are not pretty sure about the CG. CG variation could be there. And sometimes it is difficult to really get what is the LT we are talking about. But at a conceptual stage, what we do when you define VH, which is actually ST LT by SW C bar, which is called. At a conceptual stage, we take LT as distance between AC of the wing and AC of the tail. Right? At a conceptual stage. Okay? But you should not forget that ideally moment will come about CG because of tail. So this distance LT, distance between CG and the AC of tail is important. But we use this length. At the same time, you also know the difference between CG of the aircraft and AC of the wing will not be much, right? So it's not a bad assumption. It simplifies your approach because you are going to use statistical data. When I am saying so many things, let me erase this. I need to know roughly what is the fuselage length. Because after all, we are going to install the tail, wing, that will be on the fuselage. So I need to know where do I locate it depending upon the fuselage length. How do I get what should be the fuselage length and the diameter? Again, you understand that is decided by the purpose. If it is a full-fledged passenger large aircraft, the length will be predominantly decided by how many passengers you are going to carry, and then you have to ensure that they can walk through the aisle. So that will decide the diameter. But if it's a general aviation type, Cessna 206, hardly 4 or 6 people will be sitting, and they need not walk through the aisle. They can go, crawl in, and sit. So all these things will decide the type of aircraft fuselage you are going to design. There is an excellent statistical data, statistical guideline which is purely estimated using the gross weight of the airplane. And that is fuselage length given as L equal to A W naught to the power C. Just I will give example for sailplane, some number you can refer Raymer. This is unpowered. A and C if I write, and there is a sailplane powered, then general aviation, single engine, then general aviation, twin engine, and you can have a turboprop. Typically, the values are for a sailplane unpowered, A is 0.86 and C is 0.48. For power it is 0.71, 0.48. For general aviation single engine it is 4.37 and 0.23. And then your twin engine it is 0.86, 0.42, and for turboprop it is 0.37, 0.51. These are statistical number, and this gives excellent correlation. And please understand, when you are using this is in FPS, right? That is very important. You use FPS system. And maybe new books and everything they are giving in SI unit, but I am giving you in FPS. Let us check how does it look like. I was checking with Cessna 206 and Sinus 912. Cessna 206 like a general aviation single engine aircraft, and the weight is 3,000 pounds. So 3,000 to the power C. C is how much? C is 0.23. 0.23 into 4.37, and you'll find this is coming around 28 feet, 28.7 feet. Actual measurement I have seen, we have done it roughly, this is of 28 feet 4 inches. This is for Cessna 206. Then I was checking correlation for Sinus 912, which is a motor glider. So it is sailplane powered, and its weight is around, let me check, around 1,200 pounds. So it was, what is that, 1,200. So if it is sailplane powered, 0.71 for this, 0.71 into 1,200 pounds to the power 0.48, right? And that was coming around 21 feet, and actual measurement is 21 feet, 21.3 feet. So you see this correlation worked very well, and in the Remer's book, the author also claims this gives excellent correlation. The message is, you can easily use this relationship, this correlation in FPS unit and quickly get what is the fuselage length. Once you have a fuselage length, now where do I locate horizontal tail, wing? That becomes easier, right? You will also appreciate when some body is moving in air, especially fuselage, you think of cylinder moving in air, it is important to decide what should be length to diameter ratio so that drag is as low as possible. Right? For that, some guideline is there for a fixed internal volume. L by D 3 to 5 is good enough for subsonic. And L by D greater than 12 for supersonic. 12 or 14, these are numbers, right? So this may help you in getting what should be the slenderness of the fuselage, but do not forget one thing. If you are designing a Cessna 206, the requirement is different. There is no requirement of passenger moving through the aisle, so it do not require height. If it's Cessna 206, you have to just go inside and sit. So the diameter automatically goes down, right? So all those things play an important role when you will be actually designing a fuselage. We'll try to incorporate those things, but this is at a conceptual stage. So it's important that you know how to get a rough idea how much length will be there, right? We have just come out of the classroom because I thought we have spent enough time drawing diagrams, equations on blackboard. Let us check ourselves with whatever we have learned, how our mind gets excited when I see an airplane. For example, if I see the airplane from this angle, what is the span of this wing should be the first question that will come to my mind. And this is, I am standing near Cessna 206 aircraft, and the span is around, whatever record I have got, around 36 feet. You can easily convert it into meter. 36 divided by 3.28, it will be around 11 meters, 11 to 12 meters, around that. So that gives me an idea about what is the span, because I need to know that information. But my next question would be, if this is the span, what is the area of this wing? Because we have been talking about wing loading. So I need to know what is the wing loading of this aircraft, because that we have been talking for last few lectures. Once I know the span, I look for what is the area, and for this airplane, the area is around 174 square feet, which is equivalent to around 16 meters square. And since I now need to know what is the wing loading, so I am taking the gross weight of this airplane, Cessna 206, and the gross weight is around 1636 kg. So then gross weight is 1636 kg and wing area is 16.17 meters square. So for me, it's very easy to get wing loading. Wing loading will be around 100, 105, 110 kg per meter square. And now you can check from the statistical data for general aviation, single engine aircraft, the wing loading will be around 100 kg per meter square. So once I see this, immediately I cannot avoid looking at the propeller. One thing I see first, that this propeller, there is three propellers like that. There are airplane with two propellers. It has its own stories in terms of efficiencies and power being delivered. And if you see, as a conceptual designer, I would like to know how much is this each propeller length. The propeller length is around 3 feet. And also you know that this is a variable pitch propeller, which you know also that if I want to maximize the power at different flight conditions, so I have to fly at a different pitch angle. I need to ensure that the propeller is highly efficient at that point. Now again, recalling what we have been talking in the classroom, we are talking about thrust loading, then power loading. Since this is a IC engine backup propeller driven aircraft, we will not talk about thrust loading, so we would like to know what is the power loading for this aircraft. And the power loading for this aircraft is 12 pounds per horsepower. Again, you can check the statistical data that this will fit into whatever have been reported in the literature. So I repeat, the power loading is 12 pounds per horsepower. Now from here, I need to see also the landing gears. If you see, these are the rear landing gear. So I would like to know what is the wheelbase as a conceptual person. I am now doing conceptual design, and the wheelbase is, as per my record, is around 5.77 feet. You can understand if the wheelbase is less than a threshold, the aircraft can topple like this, right? If it is more, it is also not going to help you. So there is an optimal value as a designer you find out. Again, you use some statistical data which has evolved for a different weight class, different types of wing. Once you know what are these basic dimensions, you can easily start conceptualizing a sketch. Then you add the law of physics and make the airplane the way you want it to fly. See, once I am trying to draw a sketch in my mind about airplane, it is not only important that you know how much will be wing area or how much will be the fuselage area, fuselage volume, but you also should know how they are located relative to each other. Like if I ask you to draw a figure of a human sketch, you always try to find out what is the proportion of this size to the total size, and accordingly you make a proportional diagram so that it should look like a human figure. Similarly, whatever theory you have, conventionally it should look like a conventional airplane, right? So first thing also should come to our mind that, okay, this is my propeller, then how much from cockpit to this distance I should keep in relation to the total length of this airplane generally, for a general aviation aircraft. Just to take an example for this, the total length of this airplane from here to the extreme, that is the tip of the rudder, it is around 28 feet 3 inches. How much? 28 feet 3 inches. And from here to this cockpit here, it is roughly 3 feet 9 inches. So if you see the ratio, 20 feet is 28 feet, edit. The total length is 28 feet 3 inches, and from here to the cockpit it is around 3 feet 9 inches. So ratio is around 20 to 25%, 22% to be more precise. So when I am drawing a sketch, I know that I should keep this much of percentage for the cockpit start point, and then depending upon passenger, I will lay out the dimension. This is important for a high wing. For a conventional airplane, the high wing will start somewhere from here. So this is a very important information for drawing a conceptual sketch. Also, if I try to know if I try to find the reference from here to where do I put my horizontal stabilizer, total length was 28 feet 3 inches, and from tip to this point it is around 21 feet 6 inches. So it is around 70%, right? Okay. This is very important information when you are trying to conceptualize, and you will realize that these dimensions have important effect on the overall stability of the airplane, how we are going to design the stability of the airplane, and stability will be directly connected to handling qualities. It is also important to see what will be the CG location. We will show you where the CG location when you cover the stability part of it. Again, coming back to the wing, there is another important thing you should realize, that whether the wing is parallel to the fuselage reference line or wing has a setting angle. That is, the wing, if this is the wing, how this wing is mounted, parallel to the fuselage line, or it has been given a setting angle, which we call wing setting angle. Right? So once I am trying to see this wing, you will realize why I am also looking for wing setting angle. During our stability analysis, we will see that wing setting angle will play an important role in generating lift and control characteristics. So generally, if you are doing a conceptual sketch, it is better to keep 1 or 2 degree wing setting angle, and then final design you may give wing setting angle, may not give wing setting angle, depending upon your requirements, right? Now let us come back. We know the wing loading. You know, stall speed is square root of 2 into W by S divided by rho into CL max, and wing loading is around 100 kg per meter square. So I write 2 into 100 into 9.8 divided by rho, let's say 1.2, into CL max, I take around 1.2. So that will give you around 25, 27 meter per second. So the stall speed will be around 22, 23, and takeoff will be around 27, 28, depending upon what is the flap orientation. Right? So you could see that all these numbers are making sense based on whatever we have studied there. Okay. See, this is a very important part of the airplane. This is called stabilizer, you all know. So as a designer, if you want to conceptualize this configuration, I should look for, if this is the whole is horizontal stabilizer and this much portion is the elevator, then I should try to know what is the percentage of area being used as elevator. And from this you could see that this is around 30 to 35% of the whole stabilizer area. So when I am conceptualizing a design, I will keep around 30%, although by through analysis we will also find out that And whatever number I get through analysis, I cross-check whether I am really making sense or not, whether these numbers are coming or conforming to the conventional tail or not. Right? You'll also find there's some portion of the tail elevator is somewhere here, and why this is given. Many airplanes may not have this, so we'll talk about this portion also, how it's going to help in the handling qualities of the airplane. Since we are talking about elevator, it is important to know that where is the CG location of this whole airplane. That is also very important observation one need to have. This location of CG somewhere should be closer to this landing gear, and you understand the CG should be a little ahead of this rear landing gear. If the CG is behind rear landing gear, there will be a tendency of airplane to hit like this. And if you see the dimension here, this CG is roughly around 8.5 feet for most forward, and the landing gear is around 9 feet. Right? Okay. These are rough numbers. So what is being conveyed is you ensure that the CG is first of all near here where the people are sitting, cockpit, etc. is there, and that CG location should be little aft of the rear landing gear. Okay. So that also makes sense for us. And if you see now here, another question always comes to our mind when you see an aircraft. We try to know what is the ratio of length between span and the length, right? If this is the span, what is the length? What is the ratio? Typically, for this example airplane, total length is around 28 feet 3 inches, and if you see the span is around 36 feet. Okay, so 36 divided by 28 feet, so around 70-75%. That is the ratio of the length to span. That is, you can keep the length around 75% of the span to start initial conceptual design, right? And you'll find mostly that will conform to conventional airplane. That is, the total length is around 75% of the total span. This is an important observation you must keep back of your mind. And also, another question will come to your mind: what is the diameter, maximum diameter of the fuselage? You very well understand that depends upon what sort of a number of passengers you are going to carry. But for this of a 6-seaters, for this airplane, the width is around 50 inches. 50 inches means around 4 feet, and the height is around 43 inches, which is around 3-point-some feet. So 50 inch and 30 inch, that is the cross-section width and height of the fuselage. So for such airplane, you don't walk through the fuselage, you go crumble like this and then sit. But for an Airbus or Boeing or big airplane, you need to walk through the fuselage, so their diameters are more. And so that sort of a requirements are different. But as long as you produce appropriate lift, it doesn't make much of a difference from aerodynamics point of view. Remember, we started talking about this length because we are looking for how to locate horizontal tail, what should be its size, and we decided the best way to visualize at conceptual stage is to look for VH, tail volume ratio, right? So statistical some value I will be giving for tail volume ratio, and you know what is importance of tail volume ratio. So again, for sailplane, then general aviation, then twin turboprop, then jet transport. We'll just give some representative number, where CHT is the tail volume ratio for horizontal tail, and CVT tail volume ratio for vertical tail, and we define CHT as LHT SHT by C wing S wing, and CVT vertical tail volume ratio as LVT VT by B the span of the wing SW. Please note this, vertical tail volume ratio is non-dimensionalized with span, in contrast to horizontal tail volume ratio, we try to non-dimensionalize using chord, mean aerodynamic chord, more precisely. Right. So these values are, it is around 0.5 for sail plane, 0.7 for general aviation, twin turboprop 0.9 and 1.0, and this is 0.02, 0.04, 0.08, 0.09. These are conservative numbers, especially here. These are conservative side. Okay. But at a conceptual stage, okay, you use that. There will be a question how much LHT I should take historically. There are some guidelines. You understand this LHT means that LT, which is ideally it is distance between AC of the tail and CG of the aircraft. But we are, since we don't know where is the CG, we take from AC of the wing to AC of the tail. Also silently we know that AC of the wing and CG they will be close, right? For a guideline for LHT, for a front mounted engine, L you can take as 60% of fuselage length. So that is why before coming to this, we said let us see what will be the fuselage length. If the engine is at the wing mounted engine, then L you take around 50 to 55% of fuselage length. And for a sail plane, we take L as 65% of the fuselage length. So this is typically the number. Why this is important? You see, suppose I am designing a sail or let's say general aviation, right? So I know CHT is 0.7. So immediately I write 0.7 is equal to LHT. LHT I get from this. So this is known. I want to find out what is SHT. This is what I want to know. Divided by C bar, already I know wing I have designed, at least conceptualized, wing area I know. So you can easily find out how much tail area is required at a simple conceptual stage. Then what a designer does, whatever number it comes, he checks what is this percentage of this tail area in compared to the whole wing area. So there are statistical data also will be there. Is it 15%, 20%? Or is it only 4%, 2%? So that also gives the designer a feel whether he is in the right direction or not. Right? We will be talking about that as well. But this is just telling you how do I get first number. Then there is a process of checking whether at an intermediate stage am I going right or not. There this statistical data gives you lots of help, and that is again and again I am telling you need to have a baseline aircraft always beside you to check whether you are in right direction or not. Right. With this background, now we will become more specific on how much will be the elevator area, how much will be the aileron area, how to decide at a conceptual level, how much should I take a rudder area, so that with a pen and pencil and a small this information, I should be able to sketch my first conceptual aircraft where sizes are proportionate. Right? Then we go for final analysis. and do refinement. So maybe another 1 or 2 lecture I will take on how to get into all these numbers, and you can at least draw a good sketch of an airplane which looks proportionate. Okay? Thank you very much.